Hey everyone, welcome to chapter 7. We're going to be first talking about exponential growth and decay, and then later on in this unit we'll be talking more about logarithms and doing problems along those lines. All right, let's start. Let's introduce ourselves to exponential growth and decay. So exponential equations in general have this form: y equals a times b to the x. A is some number, b is some number, and then x is our variable. Okay, which makes the reason why this is exponential. It's called exponential for the reason because our variable is the exponent in all of these. Any equation that has a variable as an exponent can reference as an exponential equation. Typically, in these functions, a is usually referencing kind of your starting value or starting amount when it comes to more practical real-world problems. B typically represents sort of the rate of change, if you will. It's a little bit more specific than that, but it typically references how quickly this exponential growth is growing or decaying, depending on if it's growth or decay. Now, a can't be 0, b can't be greater, or b has to be bigger than 0, and b cannot be 1. And the reasons for that is if a was 0, you'd have 0 times b to the x, and it wouldn't matter what b or x was, because if you multiply 0 to anything, it would always be 0. So that's why a can't be 0, because it would essentially make everything else useless. And b can't be 1, because if b was 1, you'd have a times 1 to the x power. And if you do your order of operations, you always do the exponents before you do the multiplying. And 1 to any power would always just be 1. 1 to the 5th power, 1 to the 4th power, 1 to the 19th power, wouldn't matter. 1 to the negative something power, it would always be 1. So a times 1 would always be a. Again, it makes the whole thing useless. So those are those parameters for those reasons. You don't necessarily have to remember them, but you should at least know how they logically make sense and why they couldn't work. All right, so growth functions and decay functions. Growth functions, as pictured on the left, this is when our b value is bigger than 1. And they typically look like this graph, where they start from left to right. It's kind of going upwards. And you can see it starts going up really slow in the beginning, but it starts picking up, getting some momentum, and then by the end of it, you can see it's changing and growing really, really quickly. Same thing for decay, except kind of in the reversal. It decays pretty quickly, but it levels out over time, and it starts decaying less and less and less as you move forward. All right, and again, this is when b is less than 1. Now again, b still has to be bigger than 0, but b is less than 1. So these are typically numbers like fractions or some weird decimal values, but those would typically be decay. All right, so mentioning growth or decay, let's just identify which of these is growth, which of these is decay. Remember, our equation is a times b to the x power. And to determine whether it's growing or decaying, all you have to do is look at the b value. We mentioned before that its growth if b is bigger than 1, and decay if b is less than 1. Now again, b is still bigger than 0, but the idea is that b is less than 1 would be decay. So our b value is 1.2, and last time I checked, that's bigger than 1, so that would be growth. 0.9 is our b value in the second problem, and last time I checked, 0.9 is less than 1, so it's decay. And that's all it comes down to, is these b values. 1.54 is bigger than 1, so it's growth. 0.70 is less than 1, so it's decay. 2 is obviously bigger than 1, so it's growth. And 0.07 is less than 1, so it is decay. All right, a lot of real-world problems use exponential functions. Particularly in the finance industry, finance industry, anything finance, compound interest, things of those along those lines. Some people reference stock market sometimes, but there are a lot of other things like population and radioactive half-life. There's also carbon dating, things like that. All right, so now a more detailed version of our a times b to the x power. Remember, we said a times b to the x. We said it was growth if b was bigger than 1. Well, how much bigger than 1 it is going to be important. And here, again, we still have a times b to the x, but this case, we said b would be less than 1, and that's why you can see a subtraction sign there. So how much less than 1? Exactly what are you subtracting would be the rate of your decay. And for growth, how much are you adding would be the rate of growth. Okay? So A, like I said, is typically referencing an initial amount. R, in this case, would be your growth or decay rate, often given as a percent. X is usually a reference of time. Our exponent, or the variable in this case, is usually a reference in time. All right, so I want to find the rate of growth or rate of decay on these problems. And a quick way of doing that is kind of look at your function. All right, now our first one here, this is our b value. And the question you could ask yourself is 1.2. It's bigger than 1, so it's growth. We've already mentioned that. But how much bigger than 1 is it? That would be our rate. In this case, you might kind of do that math in your head, mental math. You could tell that 1.2 is 0.2 bigger than 1. So, of course, 0.2 would be our rate. Now, if you have a hard time, if you don't have the mental math, or you just get stuck on any type of problem, what you can do is, you know it's growth, so you know this is b plus 1. Or not b plus 1, b plus r. Right? Wait, what am I saying? I'm sorry. Going crazy. It's 1 plus r, right? Because it's growing. 1 plus r is equal to 1.2. If you want to just take that little equation, you could set it up, and we can subtract 1, and we could get that r would equal 1.2 minus 1, which is just 0.2. So you can always use a little equation. Okay, we'll do the same thing for decay in a moment. So 0.2 is our rate. If you want to write it as a percent, it's 20%. All right. So for decay, this is decay we know because it's less than 1, so I know it's 1 minus r. And again, if I have a hard time figuring out how much less than 1 it is, I can just take the fact that I have 1 minus r, and I can set it equal to 0.9. And then solve this. So subtracting 1, you get negative r equal to negative 0.10. And then if you want to get rid of the negative, you can divide by the negative, which would just change it to a positive 0.1. So our R value, our rate, would be 0.1. Okay, or again, same as 10%. All right, so a number in the third one, I guess it's not number 3, but the third one, we have 1.54. Again, you can ask yourself, how much bigger than 1 is this? That's my rate. And you might, mental math folks, can probably say it's 0.54 bigger than 1 so that the rate is 0.54. But again, if you get stuck and you can't remember that, which by the way is 54%, you can just take the fact that you know that this is 1 plus our rate is equal to this 1.54, and you can just solve that equation. Subtract 1, and you'll get 0.54. All right, same thing on these last ones. I'm just going to kind of quickly go over them. But this would be decay, so it's 1 minus r, which would equal the 0.70. And again, you could solve that. The answer would be 0.3, or 30%. This next one, the fifth one, is 2. Again, it's kind of almost too easy because you're kind of overthinking a lot of times, but 2 is equal to 1 plus our rate. So if I wanted to find r, I could solve that equation. R is equal to exactly 1, which is the same as 100%. And our last one, it's decay, so it would be 1 minus r, which would equal to 0.07. You can solve that, and you'll see that the rate is 0.93, or 93%. Okay? So, little things you can do to find the rate of each of these. All right, I'm going to end this video here. You're welcome to try any of these exits, or the warm-up questions, not exits of questions, if you want to, for good practice. I'm going to end it now and work on the next one. I'll see you guys later. Bye-bye.